So now we'd like to build minimal left ideals using the Clifford algebra CL6. So this is going to run exactly as we did before. So the first step that we need to do is we need to build this idempotent, or build this projector V. So this is how V is going to be defined. And again, this projector is going to behave a little bit like a vacuum state. So now to build our minimal left ideal, we do exactly the same as we did before, is we take our Clifford algebra and we left multiply it onto our projector. So we're going to call this SU. Now this minimal left ideal this time turns out to be 8 complex dimensional, and it's spanned by these basis vectors. And now we can do exactly the same as we did before, is that we're going to look at the complex conjugate space. So when we do this, we find again that we get a new space which is linearly independent from the first. And this is spanned by these 8 basis vectors. So now we know what basis vectors we have for our 2 ideals. The question is, how do we identify what these things are physically? So in the case of the complex quaternions, we had 2 basis vectors. We were able to identify those as spin up and spin down states. So we want to know now, how do we identify what these things are physically? Now you remember that we had these raising and lowering operators, the alphas and the alpha daggers, and those transformed under a U3 symmetry, which was SU3 cross U1 over Z3. Now you'll notice that SU and SD are constructed entirely out of alphas and alpha daggers. So that means that the transformations on the ladder operators are going to induce transformations on these ideals. So if we start off with SU3, we'll find that under SU3, this first basis vector transforms as a singlet. We find that these 3 states here transform into each other as an anti-triplet. These 3 states here transform into each other as a triplet. And this one at the bottom transforms as a singlet. Moving over here, this one here transforms as a singlet. These 3 here transform as a triplet. These transform as an anti-triplet. And this one here is a singlet. But this still isn't enough information for us to be able to identify what these things are physically. So let's see how these things transform under the U1 generator that we had. So you remember that our U1 generator was the number operator n. So let's see what the eigenvalues of this number operator are. So the eigenvalues of n are given by 0, 1, 1, 1, 2, 2, 2, and 3. Which doesn't look like anything special. That is until you divide it by 3. Now we have 0, 1/3, 1/3, 1/3, 2/3, 2/3, 2/3, and 1. Well, now those look like electric charges. So let's define our electric charge operator Q to be the number operator divided by 3. And let's see now how this Q acts on our states. So So for the first state, we find that this has got a charge 0. For our second level here, we find that all three of these states have the same charge, and that charge is 1/3. These three states all have the same charge, and that charge is 2/3. And this one at the bottom has got charge +1. So you can see how this is a number operator divided by 3, in that a number operator is only going to count the number of alpha daggers that we have on each level. So here we have no alpha daggers, so we get 0 charge. Here we have 1 alpha dagger, so we get 1/3. 2 alpha daggers, 2/3. 3 alpha daggers, 3/3. And now we can fill in the charges on the other side. Okay. So now we have enough information to start labeling what we have. So starting here, we have something which is a singlet under SU3 and has got 0 charge. Well, that's either a neutrino or an antineutrino. And for a reason that will be clear in a minute, I'm going to call this neutrino. So this is just a complex coefficient. Now something which is an anti-triplet under SU3 would charge 1/3. Those are anti-down quarks. Something which is a triplet under SU3 would charge 2/3. Those are up quarks. And something which is a singlet under SU3 would charge +1. That's a positron. Now something which is a singlet under SU3 would charge 0. Again, that's either a neutrino or an antineutrino. And so we're going to call this antineutrino. Now something which is a triplet under SU3 would charge -1/3. Those are down quarks. Something which is an anti-triplet under SU3 would charge -2/3. Those are anti-up quarks. And finally, something which is a singlet under SU3 would charge -1 is, of course, the electron. So we just started with the complex octonions, and we had them act on themselves repeatedly. We found that that generated a Clifford algebra CL6. And then we used a spinor construction to construct SU and SD. And we find that these states transform exactly as would one full generation of Standard Model particles under the unbroken symmetries SU3 cross U1.